When a threat like ransomware breaches a modern enterprise network, it rarely stays in one place. It moves laterally across distributed cloud environments, hunting for valuable databases and critical infrastructure to infect. Detecting these anomalies is largely a solved problem. The vulnerability lies in how systems respond. Current automated defense protocols rely on blunt force isolation tactics, like dropping entire routing tables, powering down switches, or severing connections to entire subnets. The collateral damage from this approach is massive. By aggressively cutting off a subnet, the automated defense takes down critical business flows, like payment gateways and database synchronizations. The response creates a devastating blast radius. Because the cure causes a self-inflicted denial of service outage that is frequently more expensive than the original attack, Chief Information Security Officers routinely disable these automated responses. This forces a human-in-the-loop requirement, introducing a latency window that gives the threat exactly what it needs: time to propagate. To eliminate that latency, the cybersecurity industry is eager to deploy large language models. The goal is to use the immense heuristic intelligence of an AI agent to dynamically orchestrate network topologies and generate rapid remediation scripts. But physical infrastructure requires absolute determinism, and LLMs are inherently probabilistic. They guess the next most likely token in a sequence, which means they are prone to hallucinations. In a software-defined network, those hallucinations are catastrophic. An AI might suggest attaching data paths to non-existent hardware nodes, or try to upgrade physical link capacities to mathematically impossible values, such as an IEEE 754 infinity state. Deploying those non-deterministic guesses directly to physical routers guarantees eventual failure. Organizations are currently trapped in a structural vacuum. They are caught between a highly agile, fast-moving cyber threat and an artificial intelligence controller that is entirely too dangerous to plug directly into the physical actuation layer of the network. To safely close this gap, the PTCP TNQG Enterprise Quarantine Suite begins by changing how we perceive network telemetry entirely. Look at this dashboard. Traditional systems monitor massive multimodal telemetry streams, bandwidth, jitter, and queue depth, as independent scalar variables. Watching hundreds of these separate metrics constantly spike creates severe alert fatigue, and it fails to capture how the overall system degrades under stress. The suite solves this through an information geometric transformation. It takes all of those separate, high-dimensional metrics and normalizes them, reducing them down to dimensionless link lengths. It weaves them together into a single structure. The network is no longer calculated as a vast collection of flat counters. It is mapped and analyzed as a continuous physical geometry. When a cyber attack occurs natively in this model, it doesn't trigger a series of scattered red alerts. It manifests as a physical deformation in the network's shape, a warp in what mathematicians call the Foreman-Ritchie graph curvature, which measures the physical strain on interconnected links. Translating flat data streams into physical geometry is the only way to accurately outline the exact boundaries and stress points of a hidden cyber threat. Once the geometric strain isolates the threat, an agentic AI evaluates the map and suggests a topology patch, a new routing plan to safely guide traffic around the deformed region. This diagram shows the architecture's critical safety mechanism. Instead of letting the AI actuate its suggestion on the physical network, the TNQG framework intercepts the LLM's output and forces it into a strict mathematical sandbox. Inside this isolation chamber, the system spins up a zero-copy clone of the network graph. It then runs a Boykov-Kolmogorov flow analysis, an advanced algorithm used to calculate the absolute optimal path for severing a flow, directly against the ghosted replica to test the AI's logic. The sandbox mathematically interrogates the code. It forces type coercion, chronologically sorts the commands, and applies epsilon-bound flow limits to ensure the AI's patch strictly obeys the actual physical capacity boundaries of the fiber optic cables and switches. This sandbox operates as an unyielding deterministic arbiter. It mathematically proves that the AI's bypass route works before a single line of code ever touches the physical hardware. Continuously running these complex graph diagnostics across millions of network edges requires an immense amount of processing power. Standard software configurations collapse under this pressure. They quickly succumb to Python global interpreter lock starvation, inter-process communication deadlocks, and severe memory leaks that result in total operating system kernel panics. To sustain the continuous math required for the sandbox, the suite utilizes extreme OS-level engineering. It relies on a kernel-sealed multi-process architecture built with O1 hash maps, meaning memory retrieval takes the exact same amount of time regardless of how massive data gets. It explicitly traps Linux out-of-memory errors and flattens memory complexity natively. By aggressively guarding the system's memory and file descriptors, this architectural discipline prevents asymptotic compute exhaustion. The software acts as an unbreakable cage, capable of running complex mathematical proofs indefinitely with virtually zero maintenance. In a live ransomware attack, these architectural elements converge in real time. The geometric telemetry instantly detects the structural deformation of the ransomware. The AI quickly generates a bypass route. The deterministic sandbox mathematically verifies it on the cloned network, and the system executes the minimal cut to the actual network. This entire sequence occurs in milliseconds. We can see the operational result in this visualization. The compromised nodes are perfectly isolated inside a spherical boundary. Simultaneously, critical business traffic is dynamically rerouted around the threat without dropping a single packet. By mathematically proving that a specific cut will achieve complete isolation without soldering vital traffic, the system solves the blast radius dilemma. It achieves zero entanglement with the threat, ending the requirement for a human in the loop and permanently stopping self-inflicted network outages. The implications of this framework extend far beyond enterprise cybersecurity. It offers a solution to a much larger vulnerability facing the modern world. As we view these vast interconnected satellite constellations, we are looking at the future of critical systems. The PTCP TNQG framework establishes the theoretical blueprint for how we must integrate artificial intelligence into satellite grids, national power grids, and nuclear control systems. We must utilize the immense heuristic processing power of large language models to design and optimize complex networks, but we cannot absorb their hallucination risks. Artificial intelligence must never have direct control over the physical actuation layer of our most critical hardware. The survival of modern infrastructure relies on a strict separation of powers. AI must serve strictly as an advisor, eternally caged and verified by a physics-constrained mathematical arbiter.